Thank you so much for having me. Yes, my name is Rowell, and I just moved to the Southeast in August from Montana with my family. We're still adapting, learning about what's happening here in the Southeast, and it's a whole different world, but in many respects, it's taught me a lot because I came here to learn more about prescribed fire because prescribed fire can be so limited in the West, and it's so pervasive here. Of the 13 million acres burned annually in the United States for prescribed fire, 12 million are in the Region 8 southeastern area. Florida annually burns 2 million acres, and these are numbers that are staggering because that's a wildland fire season that's done intentionally. And so it's a very powerful experience to be able to be down here and understand how a culture in the Southeast accepts fire so readily in so many different ways, and what are the lessons we can learn that we can bring back west to bring pyroculture back to the Western United States where there's acceptability for fire. I would like to also thank the Seminole Tribe and ITC for taking the time to invite us here, and I'm very grateful for this opportunity. So with that, just a little bit about Tall Timbers. Tall Timbers is a small land conservancy and research station on the Georgia-Florida border in the Red Hills of Florida and Georgia. And the story is that we manage 4,000 acres that we burn annually. And I mean we burn all 4,000 acres annually, primarily for bird habitat. And that's what defines our aesthetic. In the Red Hills, there are other historic plantations that also conserve their land in the same way. And we advocate to bring fire to those landscapes as well, to reduce fuels, hazards, but predominantly to enhance our wildlife that is very much valued in this area. As part of our land conservancy, we've created a private lands burn team that goes and helps other landowners, both private and state, to realize the benefit and the potential for fire that they can have. So we focus primarily on private lands, but as part of our mission, our board of directors has asked us to move our research to a more national scale. And so with that, we've been working a lot with the Forest Service, with Fish and Wildlife Service to start building inroads to expand fire on federal lands in the Southeast, but also begin talking about how we can expand fire in many different facets into the Western United States as well. And I acknowledge that Indigenous people are really the leaders of prescribed fire and fire management in the West. There was just recently a Los Angeles Times article that cited that the BIA reports that there's a 25% uptick of prescribed fire last year, and it's because of tribal land managers and the self-determination and the ability that they have to bring fire to the landscape. And so I feel that's very poignant to be able to bring our story of what we're kind of presenting to you so you can look at what the toolkits and the opportunities of the future might be. So historically, Tall Timbers has had involvement with the Seminole Tribe. Ticks and politics. It was the largest eradication of an indigenous species of deer in recorded history of the United States. The government had brought in different variants of cattle into Florida, and the cattle did not have an immunity to a tick fever that was basically spreading. And they did everything. They took cattle and they dipped them into insecticide to kill off the tick. And they decided that the vector of this tick fever was the indigenous deer. And so they did this eradication across Florida. And one of our founders, Ed Comerick, worked hard with the Seminole Tribe to fight for the Seminoles to retain the right. The last vestiges of this species of deer was on these lands down here managed by the Seminoles. And there was Aldo Leopold, he wrote letters in support. And so that was our historic relationship with tribes here in Florida, to fight to maintain that species and recognizing that that species of deer had a immunity to the cattle fever. But then there's this big, long, here that's 1940s, and here we are in 2019, and we're only starting to re-engage with tribal entities today. And I'm happy to say that what we're trying to do right now with the Seminole Nation of Oklahoma is a youth outreach program to bring youth to Tall Timbers to learn about pyroculture. When the Seminole were forcibly removed from the Panhandle and moved to Oklahoma, they brought clippings of dwarf willow, that they're basket weaving culture, and they transplanted those to Oklahoma. And for a while they were thriving, but as time has gone on and fire has not been used in their landscape to manage this, they're finding dwindling populations. And so they've come to Tall Timbers to ask us, how can we help in terms of bringing fire back to the landscape, being a resource for them to bring clippings of this dwarf willow back to Oklahoma to continue their traditions of fire and basket weaving. And then through the Southern Research Station, we're beginning to work with them, and they have had engagement with the Eastern Cherokee to look at opportunities on how we can bring fire back to that landscape in North Carolina. Once again, for the promotion of culturally important materials for basket weaving, for management to go and do traditional collection and fuels management and development of fuels and fire capacity for the tribe. And the reason I think this is important is because I think the other two speakers have pointed to this. We live in a landscape that is not the landscape that was given to us when we first came here. There was a landscape that was defined by the people and the ancestors of the people in this room. And it was wholly different than what we've been left with. And Stephen Pine from Arizona points out to the argument that science hasn't always been our best predictor or our best management tool because it is so variable and it changes over time. But there is a cultural memory of the landscape that's defined by indigenous people that is an objective that we can use to get the land back to the way we wish it to be or how we feel it should be. I'm just going to actually point out, this is the Black Hills, and that's the survey, Custer's survey in Chimney Rock in the 1860s, and on the right is July 2000, the same space. And you can see fire suppression and the change of the landscape is significant. If you look at the southeast, there's a long history of fire across this region. One would argue that the entirety of the lower 48 at least has a huge impact. It was defined by people, by indigenous people and their fire management for the various reasons that they do. And even in places like the Southern Appalachians in New Jersey, there is a fire return interval, and it could be anywhere between 2 to 3 years every year in the southeast to every 7 to 15 years, but people use fire across this entire landscape. And new studies point to the fact that there's just a paper that came out that it was more aggressive than what we thought, and that, as Jim said, it's not lightning-based, it's human-based. And even in the central mid-Atlantic, through the 19th century, European colonizers came in and used the same methods of fire that the Cherokee and the tribes along the mid-Atlantic used until fire suppression finally became the only method in town because of government and cultural shifts. So my question that I asked myself for this talk is, how do we intersect indigenous and Western science to manage landscapes? And in a lot of my reading that I do on the side, because my wife's involved in a lot of these things, we talk about decolonization. And I read recently this idea of indigenizing science, and that Western science can be used to help indigenize the science and provide toolkits that we train and work and collaborate with tribal entities to meet the capacity for prescribed fire, for fire management. And these can be things, the map you're looking at there was given to me by Monique Weinkoop out of the Colville National Forest, who worked with Vernon here and the Spokane and the Colville tribes to build maps of elder knowledge and oral tradition and how people reacted or felt there was best prioritization, in terms of treatments of the landscape. And I think that's the objective. The objective is that your science, indigenous science, has been tested over thousands of years, and you know best what the objectives for the landscape are. And as a Western scientist, the best I can do is work and provide tools that help you meet those objectives. And that's through collaboration, it's through talking and development. So that's what my talk is going to be about today, about kind of this future toolkit and where can we take it and how can we collaborate. and do this intersection between these two disciplines, meeting the mutual objectives, but primarily what your objectives are. So it's really the aesthetic we choose. And the reason I say this is because traditionally the land in and around Tallahassee would look completely different than it does today. Even though we apply fire every year, we have a lot of shrubs, we have a lot of regrowth. And these 4 plots here show you kind of trajectories that you see. One's a 4-year rough where you come in and burn every 4 years, and that's up here. And then we have a 3-year cycle where maybe there's a little bit less shrubs, and then a 2-year and a 1-year. Aggressive 1-years would give us, traditionally a wiregrass, maybe herbaceous forb background on the surface fuels. But we don't necessarily burn across a whole bunch of different times in the year at tall timbers because we want the shrub cover because we are promoting bobwhite quail and quail conservation. So we choose an aesthetic. It's not necessarily based off of what best science says for the landscape, but it's what science says is best for bobwhite quail. And I think it's valuable, but it's an aesthetic we chose. It's not what was there traditionally, it's just what we've chosen. And so it gives credence that if you're managing for a traditional medicinal species or huckleberry, sarvisberry, that you would choose an aesthetic and a management that would best suit the practice to conserving that species. And this kind of comes in with our wildland fire suppression. I've been watching a lot of, over the years I've watched, CSKT has a great climate change video series where they've talked with 6 elders about changes over the landscape. And a lot of it's with climate change, but a lot of it is about fuels and fire suppression because we've fundamentally changed this landscape through fire suppression, and it's not clear how we get out of it. One of the ideas is, can we burn our way out of it with more prescribed fire and building the capacity to take different risks and different ways of approaching the problem? Because, if we focus, like current fire practice or fire science focuses on like the wildland-urban interface. But in large urban areas, that's a moving target because it's always moving closer and closer into the forest, and it's harder to manage that. And so what we do is we offer fire treatments, we do thinning, and we focus a lot of money on very small areas, but not on the larger holistic landscape. And so overall, we increase risk across this landscape. And the risk might be, a lot of what I've heard, adjacency to tribal lands where Forest Service isn't treating its lands, but the tribe is. And what's the culpability of the Forest Service not being able to manage those lands, and a fire goes on to tribal lands. And so these small-scale treatments that we do in the wildland-urban interface or across field treatments are easily overwhelmed when we have those large fires. And so the traditional approach of looking at these things very myopically might not be the best. And so we're trying to build tools that give us a range of scales that we can use to improve the way we manage our landscapes. So as I said, we need more fire, to begin addressing a national wildfire problem. And fire science hasn't really met that. We've used tools from the 1960s. Most people in fire know about the Rothermel spread model. We've tried to come up with new fuels through land fire, but it's always kind of aggregating them into these generalizations. It doesn't give land managers the ability to move it into different scales and look at what is the scale of my problem and what's the data I need. And as we keep on doing this, our budgets for fighting fires are increasing. Fires go longer, and there's a lot of reasons for that. I would argue that the management type of our Type 1 teams is one part. In the Northern Rockies and in the Northwest, the Type 1 teams are using this catcher mitts approach, which is look at where the fire will be in 60 days and do 200 miles of dozer line, and that's where we'll catch the fire. And this means that we get a lot of land that might be treated through wildfire, but it also comes with a substantial risk. And it also means that we wait for these fires and we maybe do some burnouts at the last minute, but what are the opportunities that we might use to kind of expand our decision space? Whoop, sorry, wrong way. There we go. So one way would be like this is a prescription window. And with climate change, with warmer summers, drier winters, our windows are always changing. And if you look, we have relative humidity, fuel moisture, wind speed, and temperature. And somewhere, in that window is a broad range of prescriptions that we might use. But the thing that we're faced with now is that we aren't given the opportunity for trial and error anymore. New upcoming practitioners and prescribed fire trainees aren't going to get the same opportunities that their predecessors got, where you could put fire on the ground, try different opportunities, different margins. And so how do we train? How do we build capacity with our up-and-coming firefighters and prescribed fire practitioners when they don't get the same level of opportunity out in the field to work with fire? And then why is it that we only look at rate of spread or acres burned? Because there's a lot of things that happen in prescribed fire. We have different intensities. We have, changes in fuel type that in that intensity might change what the outcome ecologically is. And so we offer maybe the idea of using fire behavior as what our prescription is, because what we do is we don't just look at the acres burned, but we look at how effective those acres are and where they've burned and what's the outcome. So what I want to show you guys here is a new physics, well, it's not that new, but this is a physics-based fire behavior model. And you can kind of see it, but these are strip head ignitions on ATVs at Eglin Air Force Base. And as you see, the fire is being propagated through this landscape. It's three-dimensional. It's fully coupled with the atmosphere. So this model is not just modeling fire behavior. It's modeling the atmosphere up to 7,000 feet above it. And as you get convection from the fire, it starts sending those convective fluxes up into the atmosphere, and then it entrains air up. And this is a fully coupled atmospheric fire behavior model. I would argue the future of fire behavior modeling, because what it shows you is a realistic, real-time vision, three-dimensionally of fire that gives you, from from highly accurate fuels inputs three-dimensionally, gives you three-dimensional fire output, and it also gives you three-dimensional and quantifiable smoke output, which from a prescribed fire standpoint is really critical because smoke is one of our limiting factors. And the only problem with this model is it takes a really long time to run, like a week. And so it's not really usable in terms of operations. But there's a lot of lessons that we can learn from it. So here's an example. This is looking at that same fire from the sky. And what you'll see if the animation starts up. Can you click that animation? Or it worked on my computer. There we go. Maybe. There we go. So once again, we have a strip head fire. These are on ATVs going through a ponderosa or a longleaf pine. And what you see is the red is convective energy moving up into the atmosphere, and the blue is cooler air from the atmosphere being entrained back into the fire to feed the fire. And some of the interesting lessons of this is that here's the edge. This is, the edge of the burn unit, and all of that entrainment is bringing cool air in on the edges and wrapping around, meaning that we have less potential of spotting from this unit burning into this unit that maybe hasn't been burned. And this is a margin that can now change the way that we look at how we use prescribed fire, because it means that we can start testing assumptions about margins and risk, and maybe burn in margins that typically we thought were too risky, but through using the models and the inputs, we can test different scenarios and look at what makes us comfortable and what makes us think that maybe we would burn in something that would give us a different outcome that might be beneficial in a different way. And this has been developed through Los Alamos, which is one of our key partners. And one of the things that came up was, well, this is not operational. So the Southern Research Station and Los Alamos have now created a hybrid model, which is a, it's partly physics and it's partly probabilities, but the combustion and the atmospheric fluid dynamics are the same. So these landscapes, you can now run in what took days or weeks in minutes. So you can run, tens, hundreds of acres in 20 minutes using this. And now this is our operational approach with this, that this will be an operational version of these models that will be coming to a venue near you in the next year. We're right now building the front end to it to be able to start talking about, how do we bring this into the hands of everyone so they can change and do fire and planning. So if you talk about your prescription plan, you're planning for prescribed fires, you can use this on this model under variable fuel moistures, variable wind scenarios, variable fuel configurations, and test to see what is the prescription that we're looking for and what are the outputs. And so this is just a grass fuel, but it shows you that at 5% fuel moisture, you have broader, larger, faster. At 35%, you can't carry fire through this grass. And this is a very simple model, or simple application of it, but it's also a very poignant one because if you think trees as barriers in times when you have high fuel moisture, there'll be barriers, there'll be wraparound of the tree, or shrubs or green grass. This changes the way we can look at how we propagate fire through a landscape. So I've talked about the models, and they're developing, but the thing is that we need a whole new rethinking of fuels, and that's where I really come in. This is what I've been working on for the last 15 years, is rethinking how we do fuels. I don't go a lot into the methods, but I'll just quickly outline them. I know that if you were here for the pre-workshops or the pre-conference workshops, they talked about drones and LiDAR. But right here, this is a terrestrial laser scan, and it collects hundreds of millions of points in minutes. So we have a laser scanner that can collect 100 million points in 3 minutes. It's not for big landscapes, but for plots. And it gets, millimeter point resolution. Here in the center is a drone acquisition. And this is a 3D point cloud generated from photogrammetry structure from motion, which, as I gathered talking to people, is something that a lot of tribal managers are beginning to gain access to. Right here is structure for motion from my cell phone. So we've been going out and we've been collecting the equivalent of Brown's transects using our cell phones and just walking transects and bringing those video into the software and creating 3D point clouds of the fuel bed, but also using some classification methods to look at the distributions of live and dead, or types of fuels. And then the other thing is that we've been leveraging 3D animation and video game stuff to start creating simulated fuel beds, because the reality is that it's hard to go out and measure everything, but we can tie the 3D animation tools with a lot of our field data to start building kind of simulated inputs into what we think the fuel bed is. And some of our findings have been really good, where we've actually gotten pretty good representations of the different fuel types and the bulk densities. So with that, I'm going to talk a little bit first about kind of the scales and how they interact. So this is a landscape from the airborne LiDAR, and what you get is you get this point cloud that represents all the features above the ground and how high they are off the ground. There's a lot of data, but it's also, hard to tie like a transect or a plot to these data. So the way we like to think about it is that there's opportunities to segment the data and to train the data from a whole bunch of different perspectives. So we've used things like stem detection algorithms over the canopy height model of the LiDAR to build a representative forest of the overstory of our landscape. And This is in the Lubrecht experimental forest in Montana, but we mapped, from the laser data, all 50,000 acres of Lubrecht to a stem level to look at, what's the stem densities, and we modeled out what the, foliar biomass was, the boll volume, and then turned that into crown bulk density for our entire experimental forest. But it makes it to where you can start looking at things three-dimensionally as opposed to just plopping out 2D maps. We've also captured drone data because the airborne LiDAR data can be relatively coarse, but the drone data can get, centimeter point clouds that give you a lot of information about not just the architecture of your stands, but what the species composition is. And so we use that as well as a supplement to start training what we're seeing in these larger landscapes, because ultimately we want to have the ability to scale back and forth. You might want to sometimes model or measure a landscape. At other times, you might want to just model or a unit or a small burn unit. Then we also use terrestrial lasers, and our terrestrial lasers we look as our best representation of what's happening in a fuel bed, because once again you get millimeter resolution of data. And so this is an example of longleaf pine in Pebble Hill in some of the lands we manage, and this is a measurement. This is the bulk density at 10 centimeters, at 10 centimeter volume. So bulk density is a really critical fire behavior parameter. It tells you how much biomass you have per unit volume, and it's tied with the Rothermel and all the fire behavior models. So if you know that you have this bulk density and it's going to be this fuel moisture and it's this fuel type, it will tell you how it's going to burn. And we can take that 10 centimeter resolution data and aggregate it now to increasingly coarser scales that help us answer questions that, once again, are from plot to unit to landscape. And then we can also use the trees that we see in the landscape and use those. So we have algorithms that run up and measure the DBH at every 20 centimeters to give us not just a DBH, but a total boll diameter and the volume of that diameter, which is valuable for things with precision forestry and measuring how much merchantable timber do you have on a landscape. And we can use these individual scans to tie back to our airborne LiDAR scans to be able to now map, merchantable timber and volumes across a larger landscape. We also are adjusting the way we do fuels measurements. We've developed this 3D fuels sampling apparatus because we want to be able to have apples to apples comparisons between our fuels. So instead of doing Brown's transects and a lot of the traditional fuels, we're going through the landscape and collecting a library of fuels. And we've been funded for the next 4 years to develop a library for frequently burned southeastern and ponderosa pine forests across the United States. And so we're going in with the collaboration of the Pacific Northwest Research Station, Tall Timbers, and the Southern Research Station. We'll have field crews going for the next 4 years and collecting this method to relate back to airborne LiDAR, terrestrial LiDAR, and drone data to build a reference library. And of the properties that we'll be collecting, we're collecting surface area to volume ratios, which is critical in terms of fire behavior modeling, bulk density, as I mentioned. We'll collect particle density, which will give us ideas of what kind of fuel particles do you have, packing ratio, and these are all things that will be included in this 3D library of fuels and used as inputs to creating 3D fuels for landscapes throughout the West and the Southeast that can be used with the operational fire behavior models. And here's an example of just some raster outputs that we did at Eglin, but what we found was that we were able to map the fuel mass and fuel typing at a half meter, so 50 by 50 centimeter pixels across the landscape, and use that to train larger landscapes with really pretty good accuracy using the airborne LiDAR. And so this is like the scaling that I was talking about. We can take it from these fine scales and use now those data to train and estimate fuels over larger landscapes. But I also want to talk about the simulations, because what we're doing now is, the reason the simulations came about is because we didn't have systematic and good field data. And so what we're using now is the 3D animation techniques to kind of build scenarios and test out like what the fuels look like. And these fuels, so for every particle in there, we know what the specific mass of that particle is. So if it's a longleaf needle or a cone or broadleaf, we can estimate that, and we know it exactly, and we know the surface area to volume, and we can build these synthetic landscapes, and we can tie it to nape imagery or drone imagery, and then we can bring it into things like virtual reality. And so we've been working with the NVIDIA Corporation to integrate what we're calling FuelsCraft, and that will be that, any manager can go into this immersive background, bring in their data, and adjust it as they see fit. And then we're working with them to get the flowing physics from Quickfire and FireTech into it. So you can bring a virtual drip torch behind you and burn and show different scenarios. But more importantly, you can use it as a tool to engage with elders, to ask them, hey, is this the objective, and does this look the way we think it should look? Or community members who might be fearful of having prescribed fire adjacent to their homes. And so this is kind of the development that we're looking at in the next year or two, working with NVIDIA, is to have this Oculus Rift VR environment that you can basically go in and test your scenarios and show them visually. And so we're building this 3D fuels library for Southern Pine and Ponderosa Pine systems, and we're also been working with Region 8 Fish and Wildlife Service to create an affordable and easy laser system that they can purchase without going to competitive bid, to start doing monitoring, within the Fish and Wildlife Service, using the methods that we've been working on, and help supplement these data. And then we're trying to build these applications like with the holodeck, but what we really also want to do is provide an output and a tool that's relevant to managers. And so one of the things that we're very much trying to do is tie in with managers and seek their insight and their collaboration early on. So with that, thank you.